Good morning to everyone. My name is Greg, and today I will present a math for detecting non-Gaussian velocity distribution in galaxy clusters. Basically, I will present some preliminary results about the work that I did in the last week. Basically, we trying to translate a R code to the Python language, and the R code is made by some collaborators. Well, what are galaxy? What is galaxy? What are galaxy clusters? Galaxy clusters are structures composed by galaxies, gas, and dark matter. In this figure in the right, we can see an example of a galaxy clusters with many galaxies. We can see elliptical, lenticular, and spiral galaxies. These structures are the largest virialized structures in the universe, or almost virialized structures, because galaxy clusters evolve through the accretion of matter of their surrounding. And in this figure here, we can see 4 instances of time of the cosmic web, where the density peaks shown in yellow grow by the gravity force to higher density peaks, and in the final instance here, we can see several yellow peaks where we have the locations of the galaxy clusters in these simulations here. Because of this, we can see galaxy clusters in several dynamic stages, because if a clusters have a merger event recently, these clusters is further from the equilibrium. But if a clusters don't present a merger event recently, these clusters is more close to the virialization. Here is an example of 2 Gaussian clusters in these 2 figures and 2 non-Gaussian clusters. Why? Why Gaussian and non-Gaussian clusters are important? Because one signal of recent merger in clusters is the dynamic stage of clusters, and this leave several signals in the cluster's properties. For example, we can have substructures in the galaxy distribution in clusters. We can have higher velocities to the main galaxies, and we can have non-Gaussian velocity distributions, because in the equilibrium, we expect that the clusters tend to a Gaussian velocity distribution for their galaxies. In this figure here, we can see 2 Gaussian clusters where the galaxies follow a Gaussian velocity distribution, and we cannot see substructures. But in these 2 cases here, we can see that the galaxies are separated in minor substructures here, and here. These substructures are found using the M-class package in the R language. And we can see these substructures in the deck and right ascension and inclination, and in the velocity and the right ascension space. Because Gaussian and non-Gaussian velocity distributions can some information about the dynamic stages of clusters, we try to identify when a clusters present a non-Gaussian velocity distributions. And to do this, there are several ways, but we use the Hellinger Distance estimator. This estimator gives us a distance between 2 probability distributions. If this distribution is higher than a threshold value, we can see that this distribution, when compared to a Gaussian distributions, is not a Gaussian, and if the value of this estimator is lower than a threshold value, when we compare empirical distribution with a Gaussian theoretical distribution, we say that these clusters present a Gaussian distribution. This estimator here is introduced by Ribeiro et al. In astronomy in 2013, 12 minus 1, and used in De Carvalho et al. 2017, no, 12, no, 17, to analyze several galaxy clusters. Basically, we need to calibrate this estimator, and to do this, we simulate Gaussian distribution, generate random points from a Gaussian distribution. In this figure here, we have three examples of three generated distributions in blue with 20 points, and in the red we have Gaussian distributions that we expect. Compute the Hellinger distance for this generate and theoretical Gaussian distribution. We can see we can have a estimation for the threshold value, and we did this 10,000 times, and we estimate for each of one of them 10,000 times the Hellinger distance, shown by gray in this plot here, and we calculate the median value of the Hellinger distance and the percentiles of this value here. And we use our threshold value for separate Gaussian velocity distributions of non-Gaussian velocity distributions, the 90 percentile, shown by blue in this figure here. The work that we compare our results is the DC12. Eu sempre esqueço desse 70 in black in this figure here. Okay. When we apply this criteria here to real data, we have some like this. In these three figures, we have three Gaussian clusters classified using our method with the threshold value, and the confidence value is not higher than 90%. 90 and 90%. And in this figure here, we have three non-Gaussian clusters. We can see that we have a tail in this figure here. We have a Gaussian here and a tail here. This is not a Gaussian distribution, and this is still not a Gaussian distribution. But we need to quantify this difference, because this cannot be a work. And when we compare our results with the DC17 work, we find results very close, and we can see a slow difference in the Gaussian, and you see it's unclassifiable. But this is explained by the difference in the threshold values, because we recalculate these values. Thanks for attention.